Good afternoon, everybody. We'll give it just a few more seconds here and then we'll start in case we have any late joiners. Okay, well, let's begin. So good afternoon, everybody, and welcome to our second Tech Tips webinar in our series of Tech Tips webinars. We hope everybody had a happy, fun, and safe holiday and New Year season. We're glad to be back, and we're excited to continue on with this series. Today's webinar will be focused on the pressure limiting process. Presenting with me today will be Bill Galla, Vice President of National Sales, and Hank Sorgen, our Lead Technical Development Engineer. At the end of the presentation, we'll have a question and answer session. We have some pre-asked questions that we find to be most commonly asked on the shop floors. But in your chat box, we encourage you to also ask questions, and we'll get to as many as we can. If for some reason we didn't get to your question, don't worry. We have it and we'll follow up offline. And you can also ask the question by going to our website, which is www.prlresins.com, or you can send us an email at info@prlresins.com. So without further ado, I'd like to jump right in and start with the presentation. Hank?
Hey, thanks, Todd. Good afternoon, everybody. I hope everybody's doing well. Welcome to the second installment, as what Todd had said, our Polymer Resources Tech Tips number 2. Today's topic is going to be on the pressure limited process. So, thing that I run into a lot while troubleshooting quite often, majority of these instances, the molder isn't even aware it's happening. So having an understanding of what a pressure limited process is and how to avoid it is very important. So let's get going. First off, understanding the importance of pressure, temperature, and timing, and how they all impact each other. As a molder, the name of the game is controlling viscosity. Viscosity is controlled within ideal limits, then producing parts will be repeatable and consistent shot after shot. There are two main variables we can use as molders that will influence viscosity: temperature of the melt throughout the process and the injection speed. Different speeds will have an influence on shear heating, which in turn will impact viscosity. So as plastic flows through the channels, the gates, the cavities, there's multiple phenomena affecting the flow of the material. So let's consider flow in a runner. As the molten plastic enters that runner, it has an initial temperature and a pressure. The mold, much colder than the hot molten plastic. So as that plastic flows through the runner, because of drag and frictional effects, there's a loss of the applied pressure at the flow front of the plastic. Additionally, as the plastic hits the walls of the mold, it begins to cool. This increases the viscosity of the plastic and thereby requiring additional pressure to push the plastic. The skin of the frozen plastic that is formed on the outside of the wall decreases the cross-sectional area of that runner, and that again requiring additional pressure to keep the flow going. So here we have some images. You can see our typical laminar flow and how that flow front works its way to the side, and then you get the frozen layer against the mold steel, and you can see we're reducing the cross section there of the runner and actually requiring more pressure. So all these factors show that with increasing flow lengths and fill times, the plastic needs more and more available pressure to maintain the required flow rate or injection speed that the injection unit is trying to achieve and maintain throughout that entire filling phase. This results in the reduction of the pressure at the head of the flow front and is called a pressure drop. So a little analogy for our pressure limit. Say you're going down the highway, you have your cruise control in your car set at 65 miles an hour, you're on a nice flat road. The RPMs, they pretty much remain the same as you're on cruise control, maintaining that same speed of 65. Then you're approaching a big incline, a grade, a big hill. The car needs to maintain the same speed of 65 per that cruise control setting. As that car enters that incline, the motor will increase its RPMs to provide more power to the drivetrain to then maintain that 65 miles an hour. So the car's power has been increased to maintain the same speed. Let's look at this as the power of the car as the injection pressure available from the injection molding machine, and we'll look at the cruise control speed as the set injection speed or flow rate. The steep hill, the steep grade, that's the resistance and flow that we're hitting as the filling stage progresses and the flow front begins to cool off. All the resistance we're going to be going against. So the molding machine has a limited maximum amount of pressure available to push the screw at a set injection speed. The required pressure to push that screw at the set injection speed should never be more than the maximum available pressure from the machine. Molding machines have a control setting to where a pressure value set point can be entered to allow for a maximum injection pressure limit. It needs to be understood that this is a limit, and it does exactly that. It limits the amount of injection pressure allowed to fill the cavity, a cutoff point. I don't know how many times I've seen people walk in and they want to add more volume in the cavity. So they increase their max injection pressure limit, and they think that's what adds more plastic into the cavity, where in reality, they have a pressure limited process. As you can see in this graph here, we have our injection pressure trace, and then we have the yellow line. That is our max set limit. That's our actual setting that we entered into the machine. And here in this case, the machine we're using has a maximum available pressure of 20,000. So we are pressure limited in this graph here because we're hitting our own limit. So this is pressure limited process based on hitting our own limit. There's another form of that, and that is the molding machine will not allow the injection pressure needed to fill the cavity exceed this set limit, and will flatline as at this limit as it was told to based on the pressure value that was entered. Having a peak injection pressure that is meeting or exceeding this limit is a pressure limited process. Not to mention running a process like this at the max limit on the machine's end. So in this case, not only are we're hitting the actual max machine pressure limit of the machine, and we have our limit set to it. So we're at 100% of what's capable. In the long run, you can do some damage or potential wear and tear on your machine. You think we have these big, powerful, torquey, expensive servo motors driving all this. You can potentially overwork them, especially if you're at the high end of this machine or the limit here. And eventually that can cost you some serious money and potentially lead to some premature failure. So it's good not to really beat your machines up if you can help it. So an example, so let's say hydraulic machine, its max available hydraulic pressure, 2,200 PSI hydraulic pressure. In order to move the screw at 5.5 inches per second, we'll say that's our ideal injection speed, it will require 2,500 PSI. Then we can never achieve the required speed of 5 inches per second. The maximum pressure will be used, 2,200 PSI will be used, but we're not going to get the speed that we want. It'll never be achieved. So that is being pressure limited. So moving on, pressure limited process and viscosity shifts. With a pressure limited process, the slightest viscosity shift can go unnoticed by the process tech or the operator, potentially resulting in some short shots or overfilled flash parts. While running a pressure limited process, if an increase in viscosity occurs, the maximum injection pressure limit set point will be reached sooner. Though this is still pressure limited, there is now a potential chance of decreasing that first stage fill volume, and you'll be putting less material into the cavity prior to that second stage pack and hold, possibly causing short shots, non-fills. While running pressure limited process, if a decrease in viscosity occurs, the maximum injection pressure limit set point will be reached later in time or not at all, It may become no longer pressure limited, but regardless, if the limit has been met or not, the first stage fill volume may have been increased, putting more material into the cavity prior to the second stage pack and hold. This will possibly cause an overpacked or flash part. It's always good to go back and re-verify that first stage fill. So non-pressure limited processes and viscosity shifts. So having a machine's max pressure limit set above the actual maximum injection pressure, the peak plastic pressure, will allow the processor and machine to observe or detect any fluctuations of injection pressures or fill times that would indicate a shift in viscosity. So here we have a non-pressure limited injection trace here, where you can see our peak pressure is just above 16,000 PSI. Our limit is set probably around 18,000 PSI, and our max limiter machine is 20. So we are not hitting either of these limits. And you can see now that we're not limited, we no longer flatline with that curve. We hit our peak and we can drop off from that first stage to the second stage pack and hold. So while running a non-pressure limited process, if an increase in viscosity occurs, the maximum injection pressure limit may not be reached if it's a minor shift in viscosity. It's pretty common. The variance can also be observed and recorded on the machine, notifying a process tech or operator of that shift. So an example of a major shift, give a big shift in melt flow rate, and though it is also possible that the limit may be reached if the viscosity increase is significant, even though less common, it can be noticed and observed on the machine, informing the process tech of a major change or a shift in viscosity. The same yet opposite effects would be applied to a decrease in viscosity on a non-pressure limited process. So suggestions to avoid this dreaded pressure limited process: utilize decouple molding first and foremost. You can take off your second stage pack hold, confirm that your first stage is not pressure limited, and then you can adjust accordingly to get the volume filled you want. You can play with your speeds, confirm first stage is good, and then you can turn your second stage back on, even though it may need to change as well. Okay, if you're experiencing pressure limited process, here's some values you can try adjusting. I'd recommend independently. Doing multiple things at once usually doesn't lead well and won't tell you what truly had an impact or resolved an issue. So one thing, melt temp. You can increase your temp. It's going to decrease your pressure, but I'd still recommend referencing the material data sheet and the recommended temp ranges. First stage fill rate, your injection speed. You slow your speed down, you're typically going to reduce your pressure as well. Again, if you're changing your first stage speed, would still recommend confirming, taking pack and hold off to see where that first stage fill truly is from a volume perspective. Another thing you can do is conduct a pressure loss study to determine any restriction points throughout the feed system, the nozzle, the sprue, runner, the gate. And then you can, once you find out where those restrictions are, you can increase size accordingly to help decrease that pressure and have a good stable pressure drops across the board. Lastly, another thing you can do, move to a different injection molding machine that enables a higher range or limit of max injection pressure. I know this is not always an option due to resources and machine availability, but it typically is going to be solvable for that part. If you guys have some extra time, I highly recommend checking out this article that can be found here on this link. It goes into more detail of pressure loss studies. So good read, highly recommended. So one thing I want to stress, utilize the machine's pressure curves if available. Most machines today have this, though you may not have that luxury on some of those older dinosaur presses. In that case, it's good to note and record your peak pressure values during fill. Also, take note of those peak pressures all the time when you're running. Make sure it's consistent and repeatable, because you want to know what the peak pressure is, where that peak pressure happened, i.e. fill time typically. These things should be recorded and traced, and that way you can indicate if anything had changed from prior to.
All right. Well, excellent information. And I'd like to now turn it over to Bill Galla, who is going to go through some of, again, the most frequently asked questions that we hear on the shop floor. Bill?
How can you tell if my process is pressure limited on my machine?
So if your peak injection pressure is exceeding or equal to the max injection pressure setting limit or max limit of the machine, that's how you know you're pressure limited.
Thanks. The process is pressure limited. What can be done to reduce the injection pressure?
Two things that you could potentially do is increase heats within limits to try to reduce that viscosity. Another thing would be maybe slow your injection speed down to try to reduce that pressure as well.
Nice. The process is pressure limited, and I've tried all the attempts at the press to reduce pressure. What should be done next?
The next step that should be taken is conducting a pressure loss study and pinpoint those areas of flow restrictions. Once you locate those restrictions, address them by increasing their size. If they're still limited, try running in a machine with a higher injection pressure limit range.
Is there anything PRL can do from a compounding perspective to help reduce pressure?
Yes, though they have limited impact, compounding in lubricant additives can offer some relief. Also, specific melt flow ranges can be targeted when compounding those end product lots and batches.
When does one typically see the highest injection pressure during the molding process?
It's typically at transfer. So when we switch over from first stage to second stage, that's typically where the cavity is most full, and that's where you get the most pressure put back.
Thanks, Hank. We did not see any additional questions in the public chat, so I'll turn it over to Todd, and he can obviously wrap this up as well as give you some contacts to send questions as they come in.
Well, yep, we didn't see any questions today, but I'm sure there are questions out there. So again, if you do have them, please email them over to info@prlresins.com, or you can also find the Contact Us form on our website, www.prlresins.com. So again, we thank you for your time. We hope you have a great start to 2021, and we look forward to working with you in the future. Have a great rest of the day.